I'm Silvio Baldassarra, Chair of NORR, founder of NORR Ed, and your host. NORR is a continuing education program founded 16 years ago with three main goals: to teach, learn, improve, and to do that continuously. The program relies on bringing the best guest speakers in three main categories: architecture, engineering, and masters. Each of the NORR Ed virtual sessions since 2020 have been recorded and are available on NORR Ed YouTube for global access. Over the past 16 years, NORR Ed has hosted more than 110 leading guest speakers. Welcome to the NORR Ed offices and invited guests. Welcome also to the students of the 14 schools of architecture from Canada, the US, and the UK. This NORR Ed is in collaboration with the Faculty of Engineering at the University of Windsor in Ontario, Canada. The world's first retractable stadium roof session today starts with post-university membership. Mentorship, by definition, a mentor is someone who teaches and gives guidance to younger, less experienced, and often younger person. Not everyone is a mentor. I've had 4 mentors, and 3 of those are in the image that you're looking at. Left to right, Bill Niche, the N in NORR, who hired me in 1986 to be the roof architect on SkyDome, and with who I managed a number of complex projects throughout my career. Mike Allen from Magillian Allen Rubely, the structural engineer for SkyDome, who I worked with on SkyDome for over 3 years. And far right, Rod Robbie, the SkyDome design architect that I worked with on the development of the retractable roof and went on for 15 years pursuing stadiums globally, and my friend. All these years later, the membership from each has influenced me in my career, in my architectural and engineering design management and passion I have for the built environment. This image for me is in a sense why I have pursued with NORR Ed to teach, learn, and improve every day. Learning does not end when you graduate or become chair of a company like NORR. It simply continues forever. In 1986, after 14 years with Joseph Bogman Architects, I joined NORR as a project manager to be the project architect for SkyDome roof. Since then, I've been involved in the design and management of large-scale projects like the Ontario Court of Justice, which opened last Tuesday, where we partnered with Renzo Cano. I graduated from George Harvey Secondary High School in architectural drafting in 1969, significant because the school was actually designed by NORR's predecessor firm, John B. Parkin. Then an architectural design diploma in 1972 from Humber College, and finally a Bachelor of Architecture in 1976 from the University of Toronto. In 2020, I received the RAIC Fellowship, and today, I am chair of NORR with 14 offices globally and manage and host NORR Ed, which I founded 16 years ago. Today, I'm a little older and I will present SkyDome, the world's first retractable roof stadium, followed by a panel discussion. This is an image of SkyDome under construction. This is the areas that I'm going to cover today. I'm going to do a bit of an introduction. I'm going to talk about the roof support, the roof movement system, the roof seals, the stadium lighting, and the roof catwalks. This is just some of the areas that I basically managed for 3 years. I'm going to go back a little to Maple Leaf Stadium, 1926 to 1967. And this was at the foot of Lakeshore in Toronto, and this was baseball in Toronto at that time. Obviously, open air stadium, and as you know, many of the stadiums today for the American League have returned to open air stadiums. And this was at the time one of the major leagues in Toronto. But this is unfortunately what happens when you have baseball in a climate like Toronto, where you're susceptible to snowstorms. Like most of you know, in Toronto, we had last Friday. In 1977, the team was moved to Exhibition Stadium, and it survived there from 1977 to 1989. And you can see, being right off of the lake, the effect of, and what you're looking at is snow in the outfield. So the city turned to, at the time, a competition for a retractable roof stadium. And these were the 4 submissions. Obviously, the Robbie Gillian NORR Consortium, top left, Webzerac Menkes Housden to the right, the Bregman and Hammond scheme to the left, bottom left, and the Krang and Bulk scheme to the bottom right. The main objective of the competition was to have a field that was 100% fully exposed, and you can see which ones were 100% fully exposed. And of course, the budget of $175 million in 1985. As the entries were all evaluated, the RAND Consortium one was the one that was selected and won that competition. The project itself was at that time was a mammoth project. 125 people in the client group, 37 firms. There were 23 firms involved in the designers group with 183 people. And on the building side, 15 firms, 692 people. Over 1,000 people were involved in this project. And this gives you an idea of the build design with Ellis Don, Dominion Bridge, Laurley, the stadium roofing, and Siemens toward the movement system. And our design team with Rod Robbie, Mike Allen, Joe Carr leading the roof movement systems, and Steve Seifert on the Ellis Don side. So the interesting thing about SkyDome is it was not only a baseball stadium. And as you can see here, the blue seats, if you watch the next slide, actually retract, and they actually move over for football. So it actually was built for baseball as well as for the football team, the Argos in Toronto. And I'll get to this in a moment, but the building actually had a number of radius points. So although you think it's a complete circle, it is a circle on the outside edges, but certainly the geometry of the building was not a complete circle. This is a section of the building itself. And how big is it? There's the Coliseum, and you can see how big the actual building is itself. So the world's largest stadium with a retractable roof, an 8-acre roof that has to open in 20 minutes, and no examples to look at. When we started, it was fairly interesting because there was quite a definition on what the roof needed to do, but there were very few drawings that we actually had to actually move forward with. So the $175 million competition budget did not, and this was controversial after the time, did not include a number of things. In fact, in 1989, the building was a $500 million building. And how does that translate to 1923? $1.8 million. So there are things that were added, such as a hotel that was never part of the original competition on the north end, a first in a stadium. And there were a number of miscellaneous things. And the roof was also an add-on that was not part of that original budget. These are things that were actually in the competition that people found a bit of a surprise, but it was in the competition budget. So what were we looking at? We were looking at something that had never done before, and I use this image because there was a lot of testing There were a lot of innovations that were done in SkyDome that go back to testing and trying things and failures that I'm going to talk about. And this image, this Frank Lloyd Wright image of the lily pad really talks to that. So the very first thing that I really started looking at is, I was charged with managing the roof. And the first thing I needed is roof supports. And obviously we had just won the competition. I had just started and there were no roof supports. So we started looking at the roof supports. So the scope, it's an 11-ton roof that actually moves. It's not a static roof that sits on a building. In the closed position, it spreads out to the edges. It opens and it has 4 panels. And in the closed positions, it sits on the roof, but in the open positions, they're all stacked one on top of the other. And in between, it has a variety of different positions that it's in. And significant from a structural and engineering point of view, this is a 1 in 100 year return. If you're familiar with building code today, you're dealing with 1 in 50 year return. So it's twice as much as any other building. The design, 210,000 tons of concrete, and that's 2 times more than the CN Tower. And then we're dealing with what I had never seen before, a 55M bar. And that's a large reinforcing bar that you're dealing with, where you're designing concrete and you're trying to put a 55M bar into it. And then we had anchors for the rails, 4 circular expansion joints. We actually had somebody that spent 2 years designing the expansion joints on this building. And the solution had to be efficient support design that uses the minimum rebar and the minimum concrete. And here you can see the concrete and how it interacts with the steel of the roof. And here you see the concrete. All of the roof was erected on the north side of the building, 1 panel on top of the other, the first panel, and then the subsequent panels being erected on top of that first panel. Here you see a plan of the building, 51,000 seats in the baseball mode, and you see the seats down below set up for baseball mode, and 53,000 seats for football. And you see the seats that are rotated for football. So radiuses, 11 radius points. And you may ask, why are there 11 radius points? And these were all a result of sight lines for baseball and football. And we actually had 2 people that spent the entire 3 years figuring out the radius points. Now you have to remember, this is the mid 80s, so there was no Revit. This was all manual. It was people using logarithms and manual work to actually calculate all of these angles in our design, and it was all done manually. So we ended up with a design that had 11 radius points, which complicated the entire design. These are the bents, and every single one of these bents, every 3rd bent went to a different radius point in the building. And here you can see the construction. And now we get to the roof. So the roof, one of the first questions that I asked of Mike Allen's structural group was, can I have the structural drawings for the roof? And they said, we have a general drawing, but here's a book of XYZ coordinates. And because the roof was so complicated, it was done from a software point of view. And I had XYZ coordinates, and architecturally, we ended up drawing architectural drawings of what the roof was all about. But one of the things that I started off with is how the actual roof works. So there's panel 1, which is a quarter dome, panel 2, which is a barrel vault, 3 is a barrel vault, and 4 is the fixed panel, but it's not actually fixed. It actually sits on bearings. And it's the quarter dome at the north end that doesn't move. And if you see the dotted lines, these panels all move and they end up on the north end of the building. And that basically was part of the 100% field being in full sunlight. In the other direction, you can see the barrel vaults, the arches of the barrel vaults. And significant is the fact that these are arches. And understanding arches, the forces of the arches, want to project out of the building. Our sight line was here, so we didn't really have any room here to do, if you understand flying buttresses, Notre Dame, and the Gothic churches of the world. There should have been a buttress here to take the reaction of the force of this arch. What structurally it actually happens is that force is actually taken into the concrete in a reverse fashion and tied in back into the structure in this direction. However, the force of the arch comes in through this direction. So that was sort of one of the first lessons that I learned, and I took that. The other lesson, and you have to remember, this was a design competition, and a lot of this information we didn't have during the competition. Not only did the architects and engineers not have this, but neither did Ellis Don, who put in fixed price for this building. And this is the wind tunnel at RWDI in Guelph. This was done well into the first and second year of us working on this building. And this is the wind tunnel that talked about the forces on the building. But more significantly than the wind is the snow and the snow loads. And I'll talk about this a little bit later, but the surprise that we had was that you would expect on an arch and a dome like this, that the snow loads would actually disappear and blow off of an arch like this, but you can see the accumulation of snow right at the top of the arch, which is probably the worst place for a snow load on an arch, and the amount of snow, and especially on these two longest panels, and the amount of load that brings down to the edges of the actual building, and the amount of buildup down in this area, which is a huge problem. But this snow load that you see here created a number of problems, both in the snow loading and the actual design of the roof members, but in the seals that I'll talk about a little bit later. So the design that we had at the very beginning, which is the design that went into the competition, was that we would have the actual trusses come down to a pin on a bogie that had wheels that ran along a track, and the concrete would be basically configured in this direction. This is the sketch that I started with, which came out of the competition. And one of the things that I noticed immediately, and we started talking about immediately, is the force comes down in an angular direction, but the wheels are vertical. And I mean, you can see here exactly what's going to happen. It's just not going to work. The wheels are just going to fly right off. So there's a bogie. It's a typical bogie. It's train railroad technology. It's fail-safe. It's been around forever. We looked at a number of other potential movement systems, but we kept coming back to this system because it's fail-safe. We knew it would work, and all of the other approaches that we took, we decided that, you know, it just wasn't safe enough to go with the other approaches that we took. And I can talk about those later in the discussion period, but this is what Joe Carr's group and we felt was the safest way to move forward on the movement systems. So if you try to rationalize this, the force comes down in the trusses, especially the arches. And the right way to position that bogie and the wheels is in alignment with the force on the truss so that the wheels sit in this direction. Well, we're dealing with design build, and there's Ellis Don, and the superintendent, who was probably the strongest proponent of building this structure. When I presented this to him the first time, he said, there's not a chance that I'm going to build formwork that looks like that and pour concrete in that direction. The other problem with this is that when I drew this, Mike Allen said, you know, that slab's not actually going to work. What you're really going to have to do is put in beams that would actually take that kind of reaction that we actually have, because at this point, we actually knew what the loading was from the snow loads from our WDI, which were way more significant than we ever thought. So from a structural point of view, we needed a beam that was this deep underneath each wheel, or maybe a beam that was this deep right in the middle to take those kind of reactions. When I took this back to the superintendent at Ellis Don, he said, absolutely not. We're not going to do formwork like that. We're not going to build that. So go away. So I went away and came up with this solution where I knew that they could build horizontal formwork and vertical formwork, and that was possible. So we ended up with a design where we would take the force in here and we split it between vertical and horizontal. And we ended up with splitting the beam. So basically that wheel comes down and the beam is basically split, and that's the length of the beam that we actually needed to resist the force on each one of these wheels. That was the design sketch, and this is the actual final drawing. So this looks somewhat complicated, but it's not. It's what's actually required to resist the loading from the wheels on the actual bogie from the roof. The rest of this is all to do with the snow load. And if you saw the snow accumulation on the RWDI snow area, this is the amount that we actually need to drain that snow. So the snow comes down here and it's all picked up and the drainage is collected. These areas are for servicing so that we could replace wheels and maintain these areas. This is the upper panel. So this is panel number 2, which is the highest panel. And so that's basically the design. The one area that was somewhat different is panel number 1. Now, number 1 is a rotating quarter dome. And it's different because panel number 1 isn't a barrel vault. It's actually a dome which has significantly different attributes to it. It actually has an uplift force to it, because as it turns around, wind gets in underneath that panel as it's moving, and it has an uplift force. So it not only has an out and a down force, but it actually has an up and an in force. So it's quite complicated. So this is the final design for that panel. So it has a wheel that has an out wheel, and it has a down wheel and an in wheel and an out wheel. And the actual beam here is very, very thin. So we actually stretch it and it becomes the gutter. This one actually has the most accumulation of snow, and it becomes a very large gutter at the south end of the roof. And there is the first slide that you saw, but there is the configuration of panel number 1 with the down wheel, the in wheel, and the other 2 wheels. So you're looking at a fairly massive truck for panel number 1. And then panel number 4. So as I said, panel number 4 is fixed, but it's not really fixed. Because it's a steel dome, because of expansion and contraction, the steel will move on the concrete. So what it has is bridge sliding bearings. So it actually has bearings on the vertical and the horizontal that allow it to actually move, but it still has the same issues with being resisted both horizontally and vertically, taking the load for that panel. And that's what the configuration of panel number 4 looks like. This deep pocket here for panel number 4 is the gutter for panel number 4 because it's in the north end. When the roof is closed, this is completely outdoors, so the snow will drop in here. This is the track for panel number 1 because when panel number 1 rotates, it actually sits on panel number 4, and that's how close it actually is. There's about 900 millimeters difference, a gap between panel number 1 and panel number 4. And that's what it looks like in reality. So you can see people down in the gutter for panel. This is panel number 4. This is panel number 1 when it's in the open position. So that distance from that point there on panel number 1, when it's in the open position, to the top surface of panel number 4 is about 900 millimeters. Now, one thing I'm going to go back to, and I'm going to keep going back to this in this whole presentation, is no Revit, all manual. We drew all of this manually, and you have to remember that all of these trusses are not circular. They're straight line approximations from one member to the other. So there were a lot of, is this going to work or is it not going to work? And I can't tell you how many drawings that we did manually to, try to figure out, is it going to work? Is it going to clear? Are we going to make the clearances that we think we have? Because there was no way of doing this at the time. Today, with a Revit model, you can do this incredibly easily. Back then, it was incredibly difficult. So the roof movement systems. So 8 acres, we're moving 11,000 tons, 3 panels, resting on 1 panel. 100% of the field has to be open. 91% of the seats are in the sun. Open the roof in 20 minutes, 21 meters per minute. Design 1 in 100 year return. Carr and Donnell. Joe Carr was the lead designer on this. We looked at cable movement systems, rack and pinion movement systems, high velocity air bed. We thought maybe we can do this as a hydrocraft. Fluid bed. We thought about using mercury. A lot of lighthouses actually float on mercury. We ended up with railroad technology. The solution, eventually we ended up with 54 10 horsepower motors. They're DC motors, they're not AC powered. And it's computer controlled to avoid racking from one side to the other. And this has a great story. This is a brass model of the roof. And this was really the only thing that we did to try to check interferences. And The story about this is that it's currently, the panels are sitting in Andrew Schmidt's house and Mark Kellier's house, which thank God have not gone to, to be thrown away. But the reality is that we were never able to actually check anything because the first attempt at this model was a failure because it was improperly actually built. And by the time we actually had this model built, the roof was built. So it was a great attempt at building a model so that we could check for clearances, but we were actually never able to do it because it took longer to build a proper model than it did to build the actual building. So the panels, I'm going to take you through the sequence, and this is manual, but it was the way we did everything back in the mid 80s. So these are the actual drawings that we actually used. So as we start, the panel number 2 moves first so that it detaches itself from over top of panel 3. And at that point, there's a gap between the rotating panel at the bottom and panel 2. They start to move in sequence, and they move together as panel 2 continues to move over panel 3. And then they can continue to move. And at this point, panel 2 and 3 are over top of panel 4, completely at the north end. And then panel 1 slides in underneath panel 3 and panel 4. And it continues until it's completely stacked underneath 1, 2, 3, and 4. And that's 20 minutes. This is an image of the night we moved the roof for the first time. And what you're seeing here just barely in the images is the stadium lighting that I'm going to talk about in a little while. There's a distance between the underside of the rotating panel number 1 and the bottom chord of this panel and the top of these stadium lights. There's about a 900 clearance. The one thing to point out is that these stadium lights are on those 11 radius points. The panel is on a perfect circle, turning around. These are not on a perfect circle because they're radiating on the 11 radius points. So they don't actually sit on a perfect circle. So we had a big concern about whether or not we were going to actually hit these as we were turning around. So the night we moved, I was on the edge of this panel, checking for clearances as we moved it. And this is the sequence. So you can see what I just showed you in the drawings with the panels as they moved. And I have to say that, in all the years that this roof has been opened and closed, we have never had an issue with the opening or closing of the roof. So there's the drawing. One other point, back to Revit. We had one person in our office who spent almost a year drawing this drawing, which is a bit phenomenal. The roof. These lines that you see on the roof is PVC, it's Sarnafil. We actually invented these diverters because we were quite concerned about water migrating. We had the wind tunnel studies. We were actually concerned about water migrating from one side to the other. So we invented these V-shaped diverters, and Sarnafil actually took that idea and went on to actually make a product that actually does that a few years later. But these diverters were actually designed, and we worked with RWDI to come up with the actual heights of the diverters, which ended up somewhere around 7 inches in height to prevent the water from being blown from one side to the other because we were quite concerned about getting too much water into gutters and overflowing. Just as a point, the water all comes down to the gutters and it's taken down at one end on each side, and the actual water is taken down in a water spout that's water leader, I'm sorry, that is 36-inch diameter. So back to the movement systems. So these are the trucks, and if you can read the actual loading on the trucks and where they're positioned, and you can see the actual loading, the static factor loads change as they go from, and these are for the barrel vaults, they change as they go from one end to the other. So obviously when they're in the closed position, they're lower than they are when they're in the open position, because you've got one panel on top of the other. And the trucks, these are the drawings that Joe Carr's office handed me to work with for the concrete work that's underneath the trucks. And this is the drawing that I basically work with the rails. And these are not ordinary rails. These are MR rails, which are fairly significant. And what that really means is that this is an ordinary rail for ordinary rails, and there's a regular wheel for a train. So that's a regular. This is what you're seeing in red is an MR rail, and there's the wheel for one of our trucks. It's basically a 6-inch wheel, and it's solid. And this is our architectural drawing, and it really shows you the concrete. It shows you the middle wheel. So there's 2 wheels on the truck that come down on the MR rails. And then there's a center wheel, which is right on axis with the pin for the truss. And that center wheel just prevents the truck from sliding off. And then this shows you the servicing area, the drain, because sometimes this is inside, sometimes it's outside. And then there's an incredible amount of information here. These are the cable rails for the powering of the roof. I'll get that into in a little minute. And then these are rails. These are basically anchors for the trucks that are embedded in the concrete. So there's an incredible amount of anchorage that's in. When I was talking about the 55 M bars, not only is this concrete reinforced because it's acting as a beam to resist the load of the wheel, but it also has the 55 M bars plus the anchors, all of these anchors for the actual rails. Then I put this in, it was in the image that you saw, but these trucks, even when they're in the closed position, have an uplift wind force on them. And this is basically the design that's to keep the truck from moving vertically based on uplift on the actual truck. So it actually, this is a large plate at the end of the truck that actually wraps underneath the actual MR rail. And there it is right there. So it doesn't look like a lot, but every one of these elements, we spent an incredible amount of time working out the anchors, the piece of steel. There's the pin. This pin is an 8-inch solid pin, and there's the actual truss that comes down, and there's the middle wheel. So the roof itself, the power is in the roof. It comes in on a cable reel. It comes into a transformer. The transformer converts it to DC, and then it powers the motors that are on the actual trucks. So if I go back, the motors are actually on the trucks themselves. So everything is contained within the roof. And it's powered from a control room. The controls were actually updated about 5 years ago, but it's basically the same system. Instead of what you see here in the original, it's been computerized, but it's still the same system. Roof seals. This was the fun part of the project. So we had to seal the roof. When Ellis Dawn bid the project, they actually carried Sealmaster, and Sealmaster are one of the biggest, seal manufacturers in the world. They're out of Ohio. They do work for NASA. I mean, they were the best people to go to. And so I took a trip down to Ohio, went to their plant, and after reviewing what they could provide, they said, we can't help you. So you're on your own. So what we did was, their maximum was 200 millimeters. That's their maximum that they could actually, and I'll show you the problem that we ended up with. So we ended up looking at a whole series of different manufacturers. We actually spent quite a bit of time with Goodyear and in Ontario. We looked at fiberglass. We looked at passive urethane. We looked at pneumatic. We looked at conveyor belt material. We actually looked at all of this in-house, basically because there was nothing on the market that could deal with the issues that we had. And here's the problem. This panel rotates underneath this panel, and it has to be sealed at this point. This panel moves in this direction and has to be sealed at this point to the other panel, and this panel moves in this direction. So the seals are here, they're here, and they're here. And then at the sides, we have to seal to the building. Well, when we did the snow studies, because the snow does two things. Here, it's somewhat in the middle, but the issue was the unbalanced snow load. And we thought we had 200 millimeters maximum. The reality is that when we went through the unbalanced snow load calculations, instead of 200 millimeters, it was 750 was the movement that we had under unbalanced. So when I say unbalanced, here's what happens with an arch. So you have an arch above an arch, and if the snow is on this side, what happens is that this panel will drop, but the reverse happens on this side. It actually gets closer to the arch on the other side. So on this side, it actually drops down. So it expands. On this side, it actually reduces. In the middle, it's somewhere at rest. So the seal has to go from this dimension of somewhere around 800 down to 300 at the other side, and it has to work continuously. You can't have seals that are despairing from one side to the other. So there was this unbalanced snow load that was the biggest problem with the barrel vaults. So in looking at that, what we came up with is the final solution, and we worked with the University of Toronto with a number of different materials that we took into the lab, and Professor Packard at the university worked with us for over a year on these designs, and we ended up with urethane, half-inch urethane, and we ended up with a passive tube. And basically, these are the designs that we ended up with, and this is in the lab at the University of Toronto. And this is one of the tubes. There were two designs. This is one of the tubes that we ended up in. This was a pneumatic system. And this was a tube, a pneumatic system that was under pressure, that we would deflate when we opened the roof, and we would inflate when the roof was closed. And this was between two of the panels. So it basically inflated, and it would allow for it to be flexible between one side and the other. And then the second tube was this one, which was a urethane tube, and it was slightly different. Because these were barrel vaults, they move away from each other. So we were able to drop a leg from the upper panel in front of the lower panel. So this was basically a bubble tube that would actually compress. So it's a bit like your car bubble on your door. So that would simply compress. And this was a urethane, basically a passive urethane. This does not have air in it. It's just basically a urethane tube, which simply compresses. And it allows for the upper panel to move up or down. And this is what this one looks like. So we just had to make sure that we had enough clearances. And we took both of these two to mock up, and both of these two systems, this one in particular, which was the longest one between panel 2 and panel 3, are still in existence today. They're still working. They've never been replaced. And polyurethane is almost indestructible. And this is the polyurethane at the University of Toronto in the lab. And we did an incredible amount of testing in cold and warm, and it's it has a memory to it that none of the other materials that we looked at had. So it was a huge success. And these are the drawings that we did. There are adjustments in this, and this was not done with any company outside. We did this all internally. And then the last one. The failure was the conveyor belt material, because it's one of those indestructible materials. So we ended up, it failed in all of the other configurations where we used it, but we used it on the side, and it actually was exceptional there. So it just comes along, rubs against the concrete, and it makes a seal. So stadium lighting, I'm gonna move a little bit faster here. So 776 stadium lights, 2,000 watts each. They had to be at 32 degrees to the center of the field, 2,000 watts. So when we did the competition, the blue is what we had in the competition. And when we started developing this, Philips came along and said, not going to work. We're not going to get the lighting for baseball and football. It needs to be raised. So this is the design that we came up with. Raise it with a truss. It needed to be serviced. The lights were quite large, and you needed to flip the lights so that you could actually service them. So there are the lights. You need to get up here in a catwalk and flip them around. When I proposed that we do a full-scale mock-up to make sure that this would work, Elaston wasn't too sure that we should be doing it, but they eventually saw the light, and we did a full-scale mock-up to make sure that this worked. And of course, it did. But there are a number of things that we had to replace, clean the lenses, do things to it, because they go all the way around the building. And here are the angles. So getting back to the 11 radius points, every single one, every third bend, they go to a different radius points. And then there's that clearance that I pointed out earlier, extremely tight to panel 1, which rotates around most of these lights. There's the clearance down at the bottom. Catwalks. We need catwalks in the roof. We need to access from front to back and along the leading edge of the panels. So here, and from north to south. And when I said that the structural engineers gave me a book of XYZ coordinates. That's what a node looks like. So the node is somewhere in the middle there. I have no drawings. Quickly learned what a king post truss was, but the king post truss changed from one to the other. And architecturally, we're drawing all these things, and we have to put catwalks through all of this, this roof. And you can just imagine drawing every single one of these king post trusses and making sure that you've got clearance to put a catwalk through all of this from one end to the other. And you have to get onto this at the very bottom, so you can see the complication of getting in here and making sure you can actually get up and into this. We went down to Maple Leaf Gardens in Toronto and took a look at their catwalk, and it was simple. Unlike this, and this all had to be totally contained in the roof so that it could actually rotate and open. And then how do you go from one panel to the other? Well, here's the solution. You just simply leave a riser out. So it disconnects there. There's the seal. You leave a riser out, and then when it pulls apart, it's just missing a riser. And that was the solution. And that happens everywhere. We just leave a riser out. And the real difficult part was not only do you have to get from one panel to the other, and you can see how difficult it was getting through these king post trusses up here. One panel actually nests into the other. So in the closed position, these actual stairs actually nest into each other at the north end. And that was quite a feat. So what are the lessons? Not always about the cheapest solution, and there's probably better words than cheap, but and I think that, as a design build project, working with Ellis Don was a dream. We actually had most of our roof drawings at the Dominion Bridge plant, and we had them all up there because it made the most sense. The people who were doing the shop drawings and the roof were there. We could sketch on chalkboards and get our solutions passed, and everybody really was part of the design solution. Responsibilities. So is it architectural or is it engineering? It's both. There's no line in between. The catwalks is a prime example. Whose is it? And what we did with the catwalks, there's a lot of steel, there's a lot of metal, there's a lot of things that overlap between engineering and architecture, and both disciplines were part of that. Specified, the seal was a perfect example. That 200 millimeter seal would have never worked, so we take it away and we design it and find the best solution. And then the last point, the design build process. I've always been sold on design build. It allows you to really work with the industry to bring the best solutions to bear. And then this thing called attitude, just forget about it. People. I think one of the things was people forgot about who they were. It was about the project. It was about the best solutions and engaging people. And in the end, everybody benefits. And then this is, the yearly party, and there were 4, and what we did in the 3 years, the major 3 years, was huge. And before we get to the panel, I just want to leave you with one thing. To a lot of us that were part of this, and the people that are in that image, it still is SkyDome. And if you saw the movie Turning Red, this proves certainly to the next generation that it is SkyDome. Thank you. So I'm going to ask a number of our panelists to join me on screen. I'm going to start with, if the panelists can turn on their cameras, please. So I'm going to start off with Professor Jeff Packard, who graduated from the University of Adelaide, Australia, then received his master's degree from the University of Manchester and PhD from the University of Nottingham in the UK. He's currently a professor in the Department of Civil and Mineral Engineering at the University of Toronto. He is licensed professional engineer in Ontario in the UK and has been elected a fellow of 7 engineering institute societies internationally. Recent awards and honors include Doctor of Science degree from the University of Nottingham in 2006, Ontario Professional Engineers Engineering Medal for Research and Development, 2016, CSCE Guzarski Medal, 2011 and 2019. He is a recipient of Lifetime Achievement Awards, both from AISC 2021 and the Canadian Institute of Steel Construction, CISC. Welcome, Professor. Chris Andrews is a structural engineer, graduated from Carleton University, Bachelor of Engineering in 1979. Chris brings 40 years of professional practice in the areas of conceptual planning, detailed design and construction of buildings. He has specialized experience in sports facilities and sports stadium projects. Chris has held roles in structural engineering, includes Senior Vice President, Ellis Don Corporation, Managing Director, Canada, Hall Crow Yawleys, President Crothers of Wallace. He has acted as partner in charge for the redevelopment of Maple Leaf Gardens sports facility. Toronto acted as the site engineer for the design and construction of SkyDome. Currently, Chris teaches at the Civil Engineering and University of Toronto and Toronto Metropolitan University. Welcome, Chris.
Hey, nice to be here.
Professor Paul Henshaw received his bachelor's in science chemistry in 1982 and Bachelor of Engineering Science in Mechanical Engineering in 1985 from the University of Western Ontario. He then worked for 3 years as a designer for HVAC and industrial ventilation systems. In 1987, he became a licensed professional engineer in Ontario, and in 1988, he entered graduate studies at the University of Windsor to earn his MASc and PhD degrees in environmental engineering. He was hired as an assistant professor at the University of Windsor in 1997 and became head of the Department of Civil and Environmental Engineering in 2017. His areas of research have included biological wastewater treatment, emissions for combustion, automotive, coatings, application, and solar energy. Welcome, Professor Henshaw.
Thanks for having me, Silvio.
Philip Robbie is an architect and received his BA from Kent State University. His 35 years of international experience across all aspects of architectural practice. Mr. Robbie is an accomplished vice president and national design director for RSNH, a leading architectural and engineering firm with a presence in 77 locations and a workforce of 1,500 professionals. As a forward-thinking teacher, he spearheads the Building Design Strategy Group, driving the exploration of emerging trends and innovations and their impact on design workflows. His base of operations is situated in the vibrant region of South Florida. Welcome, Philip Robbie.
Thank you, Silvio.
So, welcome to all of you on the panel, and I'd like to start off with Professor Packer. That was a long time ago. That was a great photograph of you in the presentation. Wonder if you can talk a little bit about those days and the successes and the failures of all that testing that we went through.
Yeah, Silvio, we were a lot younger then, weren't we? That was 37 years ago. And I guess it was remarkable that you and I and Chris were so young at the time. And like many of the people on the whole job, we were all youngsters. And I suppose this was at the early days in many of our careers. I'd just recently finished my PhD on the topic of tubular steel structures a few years before that. And so I was recruited really as a sort of local expert, perhaps, on hollow structural sections or tubular steel at the time in town. And that was what the whole roof structure was made of. So there was an oversight committee, I think you remember, the Stadium Corporation, which represented the Ontario government. And they required a certain amount of testing and validation of all these design concepts, because like you said, there wasn't a lot of examples of this type of structure around. So we did a lot of reduced scale testing of hollow structural section connections, welded connections, bolted connections, under static loading and dynamic loading in the laboratory. And we made special purpose testing rigs. And this was all to check connection capacities and design principles and things like that. But then there was a lot of testing on materials as well, that we did anchor, rail anchors and bolts and nuts and washers and all sorts of steel materials. And it was surprising at the time, being the 1980s, there was a lot of material kept flowing into Canada, especially from China. And we found that the nuts would strip off the bolts, the rail anchors would strip, and the washers wouldn't have the right hardness either. They were soft. And so we would actually do a lot of basically proof testing. And then all of these products had to be replaced very, very quickly with high quality local products. And this was all done extremely efficiently. And so the material testing was, very interesting to sort out all these problems. And the hollow structural sections in the roof at the time were made by a company in the GTA called Sonco. And I can talk about them because the company doesn't exist now, but they were making the largest size at the largest thickness at the fastest rate they could. And so the seam welds, the longitudinal seam welds along the HSS weren't always fused all the way through. And in worst cases, the tube was actually split open. And that was how it was detected, because there were some segments of the roof actually down on the site, but luckily on the ground. And people noticed that the tubes were split open and these were about to be erected. So my goodness, what do we do? How do we fix this? And so some of these were compression members, and a tube when it's an open section is much weaker in compression than a closed section. So we started doing column tests in the laboratory as well, with split columns and closed columns. And then we could figure out how often up the split column you had to put a steel patch like a Band-Aid to close the section, so that you got buckling between the Band-Aids at a load which would represent the overall column buckling load. So this was all done at a furious rate in the laboratory. And then back out on site, all these little patches are welded in place and everything just before it was lifted up. So at times it felt like we were almost doing build design, Silvio, rather than design build. Every little thing was corrected and it was attended to. But if you're up,
just to reassure everybody, I don't know if you remember, but we did UV testing on all of the tubes, so everybody should be assured that nothing's going to fall.
No. In fact, if you're up in the 500 levels, you can see these little patches on the members where we had the problems.
Yeah.
And also these tubes were made to an ASTM A500 standard, which is rolled below normal thickness, below the standard thickness. And so the designers weren't aware that the tubes are undersized, actually, deliberately. And so the section properties get reduced. And so So this is something that we even found in the laboratories. The students who are working for me, the graduate students and the summer students, came back one day and said, after measuring these HSS members, and they couldn't find the one, what it correlated to exactly in the steel handbook. Is it this one or is it this one? It's somewhere in between. And so we said, it should be that one, but the thicknesses weren't there. So, and so this was a great revelation to the Canadian Institute of Steel Construction and the American Institute of Steel Construction. And so this is actually brought from this, we brought out this concept of a design thickness, which changed the section properties. Well, it resulted in a few members actually having to have the section properties increased as well, and the fabricator plated them and brought their section properties right up again. So I think it's testament to all this amount of quality and checking that goes on, that every little detail was checked and ticked, whereas you don't get this level of checking in a normal structure. Things just go ahead. Some rebars will get covered up in concrete, and you don't have this level of inspection going on.
Yeah, I think your point on the nuts and washers, that was a really revealing, testing that went on with the nuts and washers, because they were all sent back and they were all completely replaced before they actually went up.
Yeah,
So,
yeah, everything.
Yeah. Chris, you spent, I think you were on site during the dirty days of the dig downs and everything else, much more than I was.
The dirty days. Yeah. Well, that's one way of putting it, Silvio, for sure.
What are your thoughts from those days?
Well, I was just listening to Jeff a little bit there, and certainly listening to you. And, then I did a little quick check. It was 38 years since I started working on this darn thing. That's a long time ago, and I thought what was really interesting in the talk, and I haven't heard this for a while, was what Silvio talked about. What did he talk about? He talked about mostly engineering, I think, in some ways. Like today's talk was quite a bit about engineering and the importance of architecture. And then he sort of took one of my little points away, and it was a deep connection between engineering and architecture, this project, for sure. And in some ways, that's what kind of made it work in a lot of ways too. But I just like to talk a little bit about what I did in the context, and I'll just talk about a few stories on site, and then I'll get out of here and other people can talk too. So I was actually working on my master's at Carleton University at the time with a really interesting professor, a guy named John Agilian. And John started at Gillian Allen Rubely in Ottawa. And that was the firm that Mike Allen came from. And John was an interesting guy as a structural engineer. He actually did a kind of a PhD, not kind of, but he did his PhD at MIT in architecture and engineering. And I'd never met a structural engineer who had studied architecture before. And so we used to chat every now and then about things and designs and buildings. And one day, I'm walking by his office, and he was a short guy. I shouldn't say short, but he was a slighter sort of a man. And he had a big voice, and he says, "Chris, get in here. I want to talk to you." And I said, "Oh, okay." He says, "We just won this job." He said, "We're going to build a stadium." I said, "You want to?" And then he says, "Well, you want to work on it?" I said, "Sure." And then he says, "Well, we're going to make the roof move." And he says, "You still want to work on it?" I said, "Even more," And that was the beginning of where I started with this project. And, that day I can remember kind of walking home, and I'm thinking, I just got the best job ever. I was a young engineer. I was late 20s, I guess, at the time. And I just feel like I had the best job ever, and that was it. That was sort of the beginning of the whole thing. And fortunately, I got to work on the design of the SkyDome at the beginning. So, I had a pretty good sense of what it was all about and how it worked and what drove it and what the idea of the roof was, and, what Mike Allen was like, and quite frankly, what Rod was like as well, and what the team was like and how the team was working. And that was extremely helpful for me to take that down to the site. And my official title, I think, was, I think they called me chief site engineer or something like that for the consortium. But what I did was I kind of helped take the ideas of the design and the modeling and translate that into getting the building built. That's kind of what I did for about 3 years. And then for about 8 months, near the end of the construction and after it, because the roof still wasn't really, the project was still kind of underway when it was open. I worked on the testing of the roof and deep testing of the roof, which was really, really interesting as well too. And, you know, again, about the context of it, like this was sort of 85-ish. And the tools we had on this project were not primitive, but they were not very advanced. We were doing drawings by hand and AutoCAD. AutoCAD was new technology. A fax machine was new technology in the office. We actually had a cell phone at the very end of it, but it was a gigantic thing you wore on your shoulders, you know? So it was, the technologies were a little less developed, as Silvio was saying, than they are right now. And, you know, we had some big challenges to deal with in terms of geometry and loads. And, you know, loads, for instance, we probably had, I'm guessing, 150 load cases combinations for the roof and then the seating frame designs, you know. And now when you go into even part 4 of the OBC under limit states design, you're going to start off with about 12 of those things, you know. And so, like, how do you do this thing? How do you do this? And so the way this thing worked, and I've thought about this a lot, and, you know, and I saw an interesting video about kind of how things can work sometimes, but it was simple things. You know, we had a common goal for sure. We had a common goal of, we're going to get this roof to work. We're going to get this stadium to work. We will do it. And so we had a clear focus for this thing. We had a fairly flat communication organizational structure. I could talk to Rod or Mike any day of the time or day I wanted to. We had reasonable resources. There wasn't an endless supply of money, but there was enough money, you know, with some maneuvering to get the thing done. And then there was pretty good resources, actually good resources of people as well. And then there was a special thing that happens in some projects, and it's the kind of the good stuff that just sort of happens without planning stuff, you know, and that's, I think, an important part of some successes for sure. And part of that, I think, was this person, Rod Robbie, that came into the job, who didn't even know what really baseball was. Rod didn't know what first base was, second base was. But Rod was a leader, and Rod was an innovator, and Rod, I think, understood a lot about architecture and engineering together, which was really important. And then there was this calm, intellectual, brilliant structural engineer of Mike Allen, you know, who came up with this idea of the roof. And that wasn't planned stuff. It was just Rod and Mike, and it was John Agilian saying to Rod, who John had worked with, call up this guy, Mike, and, you know, introduce yourself to him and get him involved in this project. So that's a little bit of the context of it. So what we did on site was we built the stadium, and we had to build it fast. And we had to think about a roof that was moving in pieces. And we had to think about, like, how do you build this thing? How do you build it, you know? And in a way, that was a starting point. And so the whole idea of building it was to build it all packed up at one end of the stadium in its completely open position. That was the most compact way to kind of position the roof on the site. And that allowed a focus of the stuff that holds up the roof to happen, which is the seating frames at one end. So we just went at the seating frames at the north end, right by the railway tracks. We stacked up the roof on top of that stuff, and then we built the stadium, the rest of the stadium around it. That's kind of, in a nutshell, how it all worked. But that kind of led to some challenges as well, because, like, with the roof all stacked up and completely open, there's no way to really move it and test it until it's sort of done. You know, there's no way to move and test things until you get the rails all done and around. And so, you know, that was a big issue for sure. And, you know, there were huge challenges. And I think one of the biggest challenges, certainly I faced on site, was not so much technical, but the demands of decision-making. It was constant decision-making day and night, and it almost didn't leave you at any time. And then the other part was about communication. And in a way, I think that was the most important part about, in some ways, the engineering. Nobody taught me about communication, you know, in engineering school. The students I teach right now, I really talk about a lot, and I try and lead them in that, in the importance of communication. So that was a big one for sure as well too. But so we built at the north end. We built the frames around it. And as Silvio was saying, I mean, the roof is, the big part of the roof is a two hinged arch structure. And if anybody's a structural engineer here and, you know, they know about two hinged arches, the biggest challenge with a 2-inch arch, well, there's two issues. One is the lateral loads that come out of it. But the other part is lateral displacements, because if it displaces laterally a little bit, it induces bending moments in the arch. If it displaces vertically, it just kind of shifts down in the pins. It's not too much of a big a deal. And so we've got these massive pushes out at the top of the roof, or the top of the seating frame structure. And, you know, we've got to design and build and construct these things to be extremely stiff at the top. Not an easy thing to do. And so the design and construction of the seating frames, and everybody sort of talks about the roof, they're very complex structures as well. Reinforced concrete, but they're post-tensioned and pre-stressed. And they're post-tensioned and pre-stressed. So we had a better understanding of the deflection characteristics of these concrete structures, a lot because of the 2 hinged arches that were in the very top. And, you know, that's a little kind of quiet thing. There's a deeper story to that. And so building the roof was building it at the north end. Building the roof was building the lower part, building the second part on top of it, which was panel 1, building panel 3 on top of that, and then building panel 2 on top of the whole thing. And then moving it out, you know, one cold winter night using air-driven jacks. Building the concrete frames was an intense, challenging thing as well, because we were interfacing reinforced concrete with post-tensioning, which requires jacking and stressing and people and all kinds of things, and decision-making. And then the other part was tying the whole thing together, because the roof pushes out a lot. There's a big lateral load from that. There's big lateral loads from wind on the roof. And those lateral loads have to get down into the frames, and then it's got to get down into the foundations. And another thing, it's not really about luck, but it's about a good thing that happened there. And I'm going to stop talking in a minute, is that the seating frames actually were founded on rock. And so we could go into the rock with post-tension rock anchors and kind of tie these huge concrete frames that are getting pushed laterally right down deeply in the rock, which is a simple, clear thing to do in the way we went. And just a couple of little stories on the thing, you know, like there's all kinds of, I was thinking about this last night, and I think I'm going to kind of reflect on something that Jeff talked about. And one day, not far before it was open, it was to be open. It was, I'll say weeks and weeks. We found some bolts on the ground that were sheared, and these looked like roof bolts, and this is not a good thing. And so we went into a deep and fast and intensive investigation of that, and they turned out to be not roof bolts. They are actually bolts that were used to pull the trusses together during erection, and they're supposed to paint them bright red so that people know that they're erection bolts, and they weren't. So we kind of cleared that up, and it wasn't a problem in the roof. But while we were sorting out that, we had to figure out what to do. And so what do you do when you think there might be an issue with a bolt in the roof and you've got 50,000 people under it? How do you kind of approach that sampling? Well, the only way to do it is we tested every single bolt in the roof. We tested every single bolt using ultrasonic testing in the roof. And to do that, we had to marshal a huge army of testing people. We had to put safety nets up so nobody, if they fell, they wouldn't get, you know, injured. And we had to have a lot of communication, and we did that, and we tested every single bolt. And as it turns out, it was a bit of a redundant test, but it just actually reinforced in some ways the quality of the work that was up there. And the second story I wanted to talk about was a little thing with Rod. And Rod, great big man, great talker, strong person, strong personality, but Rod had a bit of an issue with heights. And, you know, Rod was really challenged with that. And I wasn't great about it either. I learned to walk up on the roof. And in fact, I got a video of me up on the roof while it's moving once, which was completely illegal, but I took that. And so Rod had challenges with heights. And one day he said, I really want to get up to the roof, but I can't. And I said, well, why not? He just admitted to me that he just had heights issues. So I said, come along, Rod, I'll hold your hand and we'll go up. And I got him right up to the edge of the roof where you saw that photograph from, and that took a lot for him. But I thought it was interesting that he had the kind of strength to admit that he had challenges with that. he had the strength to go up there and step over those challenges. And, you know, he did it, and he did it because he wanted to see what it was like up there. And, you know, that was a pretty special thing in some ways. There are many, many stories, and, you know, in the roof and the construction, many successes, and there were a few tragedies for sure, and literally tragedies. But overall, a fantastic project driven by a huge team of really interesting people, and a team that were completely committed to the project. And we know, you know, when I see Silvio, or I see Jeff, or I see some other people I work with, there's this kind of tight connection you have, that you've been in the trenches on something really deep and really special. And it's a great thing to kind of bring that together. That's enough for me. Thanks very much.
Thanks. I couldn't agree with you more, but when you really look at it, like, I mean, see that first slide, and it's, you know, 1,000 people, like it's 1,000 people. And I know everyone that I know or my family knows that if they had anything to do with SkyDome, they say,
Yeah.
oh, I worked on SkyDome. You know, it's like, and you say to yourself, well, what did you do?
No, I
I
know.
worked on SkyDome.
Yeah, I know. But you know who did it, though, right?
Yeah.
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 Hey,
Professor
thanks,
Henshaw.
Silvio.
Thank you. Professor Henshaw.
Thanks, Silvio. It is a very impressive talk, and this is the second time I've
Thank you.
seen it, and I'm still impressed.
Thanks.
And I think the thing that strikes me is that whenever you have a sort of a first of its kind project like this, and there's obviously a lot of engineering involved, it's, you know, you're almost, I know that it was a lot more organized, but you're almost doing it on the fly. You're almost like, okay, we've got to solve this problem, and the next day it's another problem, right? And you're just almost continuously doing that. And I want to say compounded with the fact, but maybe that's unfair, that, you know, like you say, you were doing the drawings by hand, and it makes me think of something like the moonshot, right? And the kind of development and work that went into that. And again, you know, they had slide rules, and you know, you had a capsule going to the moon that had less brains than my phone, and yet it worked. And I think it's always very impressive. And so maybe the other panelists can maybe comment on, you know, now that we have tools like the Revit and all that kind of thing, have we lost a sense of, you know, just looking at something and understanding whether it's going to fit or not, or like, are we relying on the tools too much, or are the tools just making us able to do that better or faster? Or is it really just a matter of experience? Once you get the experience, then it becomes, you become less dependent on the tools, but you still have that familiarity. So I don't know, just a question maybe for the other panelists, I think would be interesting.
Let me jump in. I have one story about that on SkyDome. So when I started, I came in and I did a set of drawings that I thought I needed for the roof, and I requested 16 people on my team. That's the very first thing I did, and they gave me 6 people. And within about a month, I figured out that the 16 people that I had, or the 6 or 7 people that they gave me, only 2 people actually understood how to design the roof, because they were the only ones that actually could visualize a roof that opened and closed, and they could actually figure out how to design something that opened and closed. The other ones just didn't understand it. They're mentally, they could not figure out that this thing was here at one time and it was there at another time and somewhere in between. And so I just said, forget it. I'm just going to work with these 2 women, and they were both women, and myself, and I started drawing, and that's what we did for the whole thing. So I think that this problem has existed forever, and I think that there are people that you know, really think about problems and are problem solvers, and there are others that aren't interested in solving problems. They're happy doing what they're doing. And the other part of this is I compare this to the Coliseum. Like, I mean, yes, we did incredible things at SkyDome, but how did they build the Coliseum? Like, I mean, that's a pretty incredible structure. I'll let the others answer.
Yes, well, students have got different abilities these days and different skills, but certainly 3D visualization is a problem, I think. So you're right there, Silvio, and also the numbers of people required nowadays is less as well. When you think of even when I think of how we would have to handwrite reports and then hand them to the secretary to be typed up and then to be corrected and then glue in photographs. So you had to get that film out of your camera, get down to a photographic lab, get it processed and fill pictures in the right size to glue them into reports and all this sort of thing. A lot of laborious work would be done in those days, which can be sped up a lot nowadays. So I think we'd probably see a lot less people now. But, the key people are still going to be ones who've got those big picture skills, the 3D visualization skills, especially.
I'd like to just talk for a minute, and whether this stays or not, but, even on that, Jeff and Silvio too, and the team. And again, I don't want to talk about the romantic old days, but when we drew stuff, and if you drew stuff by hand, you sort of learned the building by drawing it. You learned the geometry by drawing. There was this thing that happened. And you'd have it in your head, you knew what grid line 4-3 went, or AB went. And now the tools we have, as Jeff said, are extremely powerful, huge amount of data. You can get unbelievable insights into things quickly, which is way better than drawing it by hand in a lot of ways. But the really important thing I think that I've seen over sort of 35 years in a way was, in some ways, a separation between teams and architecture and engineering, although SkyDome was completely opposite to that. But I saw, certainly in my career, this separation between engineering and architecture and building trades. But over the last maybe 10 years or so, a much tighter reconnection of that. And that tighter reconnection of that engineering, architecture, building, and ownership thing, combined with the tools, I think has really opened up a huge opportunity of design capabilities and things that we can do now, which is completely fantastic. Don't know what, I was answering something there, but that's my thought. Yeah.
Philip, comments?
When I was, where does one even begin? I mean, you're amongst giants. And when this all began, I was a young man in the School of Architecture at Kent State. I was probably in my second or third year. And our two families were reconnecting. Me from the Cleveland, Akron area, and Rod from Toronto. My father and Rod were actually cousins. They both immigrated from England just after the war. And if you know anybody who served in World War II, there is a particular type of person that comes out of that war, one unique for these kinds of challenges. So that would make, I'm his first cousin once removed. And so we do share one set of great grandparents. And I think from that, I'd say that there's probably some genetic memory. They were all ship engineers. They always, were really into the technical aspects of things, and things had to work for their intended purpose. And that elegance came from the simplicity of that working component. And I think that's, that was imprinted in Rod, that was in Rod's father, that was in Rod's father's father, coming from that engineering side. So I kind of view this more from a family perspective in some ways. But there was one thing I did notice, in Rod, which I think is as valuable today as it is then, this high-tech, low-tech, no tech component. That high tech, he really understood. You talked about bringing computers in and XYZ coordinates. He really understood that high tech. The low tech, even though he was in that high tech space, he really embraced that low tech. He built models, he tore them apart, he put them back together again. He did watercolors of the SkyDome. And then the no-tech, I mean, he could articulate what it is that needed to be said. And, from that moment, he would stand up and walk towards a board to sketch something. In those 3 or 4 steps, his mind would process what that sketch needs to look like and be able to pick up that marker or that pencil and sketch out exactly what it is. And those skills today are just as valuable, that high tech, low tech, no tech. Sometimes we get enamored with just technology. There's other aspects to our profession. Let's not forget them. They've served us well throughout our lives. Rod, he would will things into existence, right? I mean, I am just going to will this into it. There is no, it is going to become real. And what you found is that, a man of commitment is the majority. So many times we sit in a room and there's dead air and there's pausing, and that was not the case with Rod around. A man of commitment is the majority, and I think those are valuable today. Shared values, as an architect, how do we reduce what we do down to 3 simple words? Well, it has to work. There has to be the context and the form. It has to work for its intended purpose. Every aspect of this has to be there, and it has to be durable. You have to understand your building sciences. Rod was really big about these things working for their intended purpose. The second aspect, it has to be in context of the client, of the culture, of the region, in context with the environment. He was really leading on those fronts. The form of it has to reflect the way that we think. That end goal is a reflection of that thought process and that shared sense of beauty. Those 3 things combined, you nobly reflect that emerging face of humanity then. And these are all highly admirable traits. And I was a witness to these things. I'm a young student in the School of Architecture living in this world. And I'm thankful for having known Rod. I'm thankful for having lived and worked in Canada. And Silvio, I'm thankful that you invited me today. I really appreciate it.
Professor Henshaw, I mean, what are your experiences with students today at obviously in Windsor at the university? How are they looking at? I mean, the one thing that certainly through our series, we're grateful to have the 14 schools of architecture on board and have a lot of contact with students. But the one thing that we've seen on a lot of the NORR eds is that there seems to be, certainly with architecture, a bit of a disillusionment with the profession and coming out, and we've had that on a lot of the NORR eds. What is your sense? I mean, obviously it's engineering, it's different than architecture. What is your sense with students right now?
Good question. We've had some recent sort of interruptions with COVID and that, which have changed a few things. But aside from that, that's just a short-term thing. It is the case sometimes where students, well, let me first by saying our top students are still our top students, and they're every bit as good as they were, and perhaps even better because they're not only bright and they can, look at some practicalities, but they can also have, work these tools that are needed for what they want to do. So yeah, that there's no question that's there. Yeah, it is the case that sometimes, there are students who are not sort of visualizing or I think was it Chris said, like, take the problem, like really, or maybe it was you, Silvio, just said, like, feel the problem, right? And really get into it. And we do find that in examples, like we have our students and they say the mechanical students, they'll build a car as part of a competition. You can tell they're really into it. They're really, they're really feeling it. And I think it's a great experience for them to sort of go through that, because it's a problem solving cycle, right? We try this, if it doesn't work, then we try something else, right? But there's a basis to it. I would say it's different. and again, aside from the short-term things, I think it would be a lot of times it would be better if they had some of these sort of low tech or no tech experiences, so that they could actually, like Chris made a really good point. When you draw that line, like it makes you know the building. It makes you know. I mean, when I started, it was hand drafting as well. I think these are good experiences, and maybe as an institution we have to sort out. And maybe we should keep some of these old experiences. Maybe we should do some, and we do that. We do some hand drawing first before we get into the AutoCAD kind of thing. So I think there are good experiences there. Students, hard to say whether they've changed. I mean, the one thing, of course, is that we've kind of downloaded our ability to memorize things to the internet. So
yeah,
there's a perception we don't need to memorize anything.
Yeah.
But I mean, it's still good to know, for example, your times tables, right? I mean, you don't want to be running to a calculator just to do a simple math. And so there is some merit to some memorization there, but by and large, a lot of students have basically sort of, like I said, they downloaded that to the internet. I heard some joke about someone who went into an interview and they had their phone out and they were using the phone to answer some of the questions. And their claim was like, well, you're hiring a package. It's me and my phone and the computer and all this. But I definitely think there's some merit to knowing some of these things and having the feel. Like that's one thing I appreciated as a young engineer, was going into the field. In fact, I asked for that so that I would go with the site inspector at our company. And when you design something on a board and then you actually see it, it really makes you understand the scale.
It's I think just touching on what Chris said, like, when you're told you're going to be working on SkyDome and you're thrilled. I mean, I had the same. I mean, when I joined NORR, Bill Niche said, we're going to bring you on. You can be a project manager on an office building or SkyDome. And I was just like, this is just no question.
Take your
Like,
pick.
project and it's actually the office building that we're in right now. Because I don't want to be a project manager in an office building. I'll take SkyDome, not a problem. But it's that excitement, and the other part of it is, when the seal didn't work, it was the excitement of
How do you fix it? How do you find the answer?
thing. It was that excitement, and we had failure after failure after failure, and you go home and you like, I'm a failure. Like, I can't solve this. Like, what am I going to do tomorrow? Like, I'm going to go back to work and everybody's going to stare at me like this thing didn't work. And it was one failure after the other until we found this great solution that's still there today. And it's that kind of excitement and drive that you realize that you actually invented something, like you did something nobody else has done. And that's true with architecture and engineering. It's not, just, and to me, it's, I mean, Chris said this later, and we've talked about this so many times. There is no line. There really is no line between architecture and engineering. And I think the more people think of it that way. I mean, we used to have a mechanical engineer in our office, and we would have meetings, and he would start talking like an architect, and you started looking at him and going like, what are you doing? Like, you're not the architect. And it was refreshing because, once you get to that point, everybody contributes to the solution, and it should be that way, but to me, it's getting that excitement and that thought process at a young age in universities, because I think back at what I went through in university, and it's all the same thing. In architecture, it's about design. It's about your design, problem. It's the end of the year, your presentation, but we didn't do structures in university. We didn't do mechanical. We didn't do electrical. Like, you did this design thing, and then you graduate, and then you get to learn about everything. So I think the more, and there are different schools, obviously. MIT has completely different programs, and but it's important to get that sort of excitement, at university, and certainly when you're about to graduate and move on and build that right at the beginning of your career.
Like I say, when the students were actually building something like, you know, that racing car or whatever, they're here till 2 a.m. They're excited. They're quite into it. Yeah. So it's
I
refreshing.
think we've got about 15 minutes left. I'm going to bring on Chad Menard, who's principal from our Detroit office. Chad, you've been looking at the questions that have been coming in. Do you have some questions?
So I do. So the first one's from Philip. So I thought I'd pull that back up. Does the roof still work today, and when was it last open? If you know, I tried to do a quick search on when it was last open, but I think it's decided on during the games. But
Sorry, what was the question? But
what was the actual question?
so go ahead, Philip. You asked the question. So
Does the roof still work, and when was it last opened?
the roof
I
still
know
work-
the
yeah, go ahead,
actual
Silvio.
date. I don't know the actual date that it was actually open, but it was open this summer for the game. So yeah, it's worked from day one.
Yeah.
It's perfectly open
Yeah.
roof, unlike the other 40 in the world. If you want me to talk about the other 40,
I set the stage for you there, Silvio.
Yeah.
Okay, I just wanted you to appreciate.
I did a quick calculation, actually. I figured it's actually moved close to 3,000 kilometers since it's been, it's open thousands of it's traveled thousands of kilometers about from here to Calgary, you know, and it still works. So, you know.
Yeah, Rod had said he actually had the opportunity to open it for the Queen on one occasion.
Yeah.
It was a special event.
Yeah.
but it's as far as I know, it's never had any issues. In fact, there was Garrick actually had an article in the paper last week about the roof, and who was the operations guy at SkyDome. And as far as I know, there's never been any issues with the
Not a big one.
opening and closing.
We actually had it stop once during an event, and we had Toronto police officers at the top to keep people from sneaking up when it was kind of under construction still, and it was still open. And the guy took his jacket off and hung it on one of the limit switches, the post for the limit switches. So the panel comes along and it doesn't trip the limit switch, and everything stops. And it's kind of at the beginning of the game, and everybody's freaking out, like, what's going on? And it was just the guy left his jacket on the limit switch. Not something we checked out. So yeah.
another question is, Silvio, there's no doubt in my mind that you thought about the various solutions over time. If you had to do it again, what would you do differently?
You know, as far as the roof, the issue, there's been a lot of controversy and been a lot of criticism about the moving systems on SkyDome. Obviously, I don't think a lot of it is warranted. I mean, the one thing that people don't understand even today is the roof loads, and Chris touched on that. It's a massive, snow loading on this roof. So I still think that the system that we ended up with on this one is the right way to go. The pneumatic seal, I think has been replaced, but the passive seal still works today. I think it was a great solution. I can't think of anything with respect to the retractable roof that I would do differently. Even the roof membrane. I mean, everybody knows this. It's had a lot of repairs because there are icicles that fall off of the CN Tower. I mean, it's right next to the CN Tower, but it's a repairable roof membrane. So even that, if it was any kind of other material, I think Chris originally wanted to see a stainless steel roof. And
Yeah, that was talked about at one time. Yeah, stainless steel. They were trying to
that would
get
have been a problem with the icicles falling off.
trying to get a nickel supplier from Sudbury to kind of donate some funds to it. But yeah.
but you know, the PVC roof is repairable and it gets repaired, and you know, so the answer to your question is I don't think we would do anything differently.
So to build on that, because I did, when I was looking through to see when it was open, I did come across that it's under renovation. So there's
Yep.
a $300 million renovation happening to the building right now. Some of the fans came back with comments, you know, they'd like to see natural grass. They'd like to, you know, better local food beverages, improved seat direction and spacing and comfort. You know, one of them, they said, bring back SkyDome, bring back the name SkyDome. So that, what would you, if you had the chance to work on this project and were able to renovate a portion of the, or some part of the building, what would you renovate? What would you change?
I think the renovations that are underway right now are adding, you know, facilities in the north end. I think they're upgrading the seats. I think they're doing the kind of renovations that are needed for the age of the building. I don't think they're doing anything massive to the building. Bringing back the name SkyDome, I think everybody has to accept the fact that, you know, there's naming rights, and that's the reality of life. But Disney, of course, you know, recognizes that it's still, you know, SkyDome. So the movie Turning Red, certainly the kids will recognize that. You know, I think to a certain extent the management of the building, it was known from day one that you know, you can't operate a building like this just on baseball and football. And now that football's gone, it's just baseball. You can't operate this kind of building. So, you know, the concerts need to, you know, bring in revenue to operate a building like this. And it really comes down to the management of the building to be able to do that. It's a difficult issue for the building. What would you do? I'm not sure, other than, you know, the seating, you know, the new seats. I think the boxes were, you know, the best boxes that were available at the time. I think those are private, and you know, those take care of themselves essentially. There are a number of sports reporters that are upset about the you know, the press boxes being moved in the new configuration, the renovations that are being planned. I'm not sure there's an answer, Chris. I don't know if you want to.
Sure. Yeah. I mean, I think a lot of the driver for the renovation away is when you look at the original purpose of the building, and the original purpose was multi-sports and multi-purpose. And the current purpose is fundamentally baseball and other events. And so that changes a lot of architectural stuff right there. And that was the basis of stadium design at the time. You know, we took that, and that was a direction from the ownership. So that's, you know, that's a lot of kind of the driver for it right now. And I think it's great that they're renovating it. You know, what's the other option is to build another one and take it down or something. And I think this tuning up renovation idea is a fantastic idea for sure.
What was the design schedule, a timeline for drawings and construction, and how long does this project go for? How many years?
It was three years, and the drawings happened as we built. Pretty much.
We couldn't, like, even if you had
There was
really good complex project management planning,
Yeah.
you know, it would be hard to do right now. And it would be hard to do with the size of the building and the changes and adding hotels and dealing with problems and challenges. But it did happen, and it happened because of the things that we talked about today. It didn't happen because of really good Gantt charts and things.
I mean, the simple examples on the double T's, and Chris and I were both involved in that. And you know, we drew the double T's, and I ended up drawing them because I was the only architect that actually knew what a double T was. And we drew them once, and then you know, Elliston didn't like the way we drew them, and we drew them twice. And then I said, well, we're not going to draw them again. And the solution was Chris and I And a couple of people at Ellis-Don sat with a set of drawings. We marked them up in red, and we gave them to the surveyor, and they actually did the drawings. And those are the drawings that they actually used to do the double teeth. That's the way we did it. We didn't have time. We
Yeah.
just didn't have time
Yeah.
to do the kind of drawings that people think that you need to do it. There wasn't an SDDD contract document. There was none of that.
It was pretty flat stuff. You know, you got a problem, you got to figure it out, you got to find out how to do it, and then you go ahead and do it, and then you move on to the next one. It was kind of like that, you know, a lot. And the other thing I'll just say about that too was at the very beginning with Ellis-Don, I can still remember the big meeting with everybody around. You know, there was the thing about the challenges and everything, and there was an agreement in that room that we were going to get it done, and then we are going to fight about it later. And that's kind of what happened in a way. We got it done, and I don't know whether we fought about it later, but you know, we kind of dealt with the hard stuff at the end, you know, rather than dealing with the hard stuff during the time. And that was really, really important too in the timing of it.
There was lots of comments about John and Jalia. And I know, Chris, you had mentioned John being
Yep.
an engineer that studied. And I know going through architecture school that we spent a lot of time studying engineering and learning
Really?
about engineering and becoming first.
That's
we
great.
have to, yeah.
Yeah.
And having a lot of professors here with the engineering students, does that happen the other way? Does, you know, I think we all need to come together and challenge each other and trust each other at the same time to come up with solutions. I know, Silvio, the rail system was revolutionary in the design of this, and I know you're a big part of that, looking at you know, architect looking at an engineering solution. So how did that interaction happen? I mean, how important was that interaction happening? How much of the challenging and trusting each other?
You go,
important.
Silvio, and then I'll talk maybe.
You know, for me, it was, this is the system that we're going to use. On the rail system, I spent all my time with Joe Carr, who was an incredibly talented engineer. His office was on Yonge Street. I spent quite a bit of time in his office and with him. And I mean, their specialty was, you know, movement system for the coal industry. And I learned an awful lot from Joe. Unfortunately, he passed away before the building was actually completed. And he had Rod, you know, like they were alike. They were totally alike. And you know, most of my rail, you know, stuff really came from Joe. And then, you know, then working with Mike on the hold downs and the anchorage systems with the rail. So for me, it was all new. I mean, it was all new, but it was an incredible education with, you know, some of the best minds in Canada. Go ahead, Chris.
Yeah, I was going to say, I mean, you know, no job is perfect, and there is friction and everything else. But I think on this one, there was no choice. Like this project, I mean, the SkyDome in some way is almost as much of a machine as it is a building. It's a machine that opens and closes and it moves over all these people, and it's heavy and big. And so the only way to get this to work and to do it in the time we had and to solve the problems was to work pretty close together. Like there was no choice to that. There wasn't some structure that said you got to work with the architects and engineer. It was one of the best projects I worked on, where we had one room upstairs above NORR's main office downstairs. And over there was the structural people, the architectural, and Silvio was over there in that corner. There was mechanical people over here. There was even construction people over in the other corner or across the street, you know. So it was kind of the only way it could sort of happen in a way. But what else, you know, started the whole thing off, I think, and I've thought about this a lot in structural engineering design, is the big idea of the thing. And the big idea was the way this roof of a half a sphere got split up with a quarter panel and these linear 2-hinged arches that moved along a linear track. And the magical part of this rotational panel, one that kind of rotated around and tucked in. And the way it not only rotates, but tucks in is a really, really complex geometric thing. And, you know, like once we sort of had that, we sort of knew we could do this as long as we could figure out all the stuff in between about the detailed engineering and how to build it, but I think in a way the team worked because we had to, and there's no choice. We were strongly committed, and it had a really good big idea, and then it had leadership from some great people too.
Silvio,
I'd love to
can
tell you stories that I can't maybe online here, but
Silvio, can you tell us a story? Because I know Paul and I were in the last kind of presentation, and you had touched on the story about the day it opened and the day you tested the roof with nobody there. It was an interesting story. If you could share that.
Yeah, it was. So I mean, basically, I think there were like 3 or 4 times that we told everybody we were going to open the roof. And then I finally got a call from Rod, and he said, "We're going to do it now." And it was like, 5 o'clock, and we rushed down there because the last thing we wanted, or anybody wanted, is media to be standing there, and guess what? The roof doesn't open. Yeah. Anyways, we went down there, and I got on top, and as Chris knows, I was in the roof all the time, and I shouldn't say this, but I'll probably get into trouble, but we didn't have tie downs or anything. We went up on the roof, and it was a different time. It was the 80s, and Don DeShane and I, he was a structural engineer, and we were up in the roof, and I had my measuring tape, and I was on the leading edge of panel 1, and I was checking the lights, and it moved, as Chris says. It wasn't under power. It was being jacked around, and it moved very slowly. But we all expected, everyone that worked on the movement system and everything, we all expected it would be like listening to the subway, moving, and
this is a big one. Yeah, this is an interesting one.
You'd feel a rumble, you'd feel it in the concrete, and so we're on top of this thing, and there's nothing. Dead silence.
Quiet. It's like a ghost up there.
Dead silence. And like this thing is moving, I'm on top of this thing, and like complete dead silence. And it was dark and everything, and it was so eerie, when it was moving. Yeah. And if you're in the building now and they're moving the building, you don't know.
You don't even know it. Yeah.
Huh?
Yeah. And
so
when we did move it the first time, when we did move it the first time, we didn't have electricity running it. We didn't have control systems up there. We didn't have measurement systems to make sure one panel didn't run into each other. We actually moved it using air compressors, high pressure air coming out of a pipe, running a torque wrench that is very similar to what the guys use when they change your snow tires. And that torque wrench went in the gearbox, and that gearbox ran the power. And that's how we ran it. We ran it by firing up a bunch of diesel engines and using compressed air to kind of move the roof around. And it was as simple as that, And we had a time we knew we had to test it. We had to move it out to kind of build other parts to it. And we had to figure out a way to move it. And that was the only way we could figure out the way to move it before we get all that electrical and computer stuff and control stuff done, which was another 8-9 months, so there we go. That's a hard one.
One last
one. So out of everything that you've done, the seals, the rail system, everything, what, the question is, never thought about it in graduate school. This has been a great precedent study for kinematic facades. Have you ever found yourselves reapplying the lessons learned from the SkyDome at smaller scale?
Yes. So we did a number of years later, I used the pneumatic seal to do a ground load bridge for Air Canada in the East Hold at Air Canada. And we used the same technology that we use for the pneumatic seal, Professor Packer, the pneumatic one that actually came over top of a CL-65 small aircraft, build a full-scale mock-up, used a furnace blower one pound pressure, and the actual seal itself, there was a series of them that came over top of the aircraft fuselage to provide cover, basically a seal for the aircraft. So when you basically blow the air into the seal, it came over the fuselage to provide cover on a ground load aircraft. And then when you turn the fan off, it retracted. So the total cost, and we did about, Air Canada put in about 14 of them in the East Hold. They're gone now because of the new aircraft. But I think the cost was $9,000 each. And, you know, regular bridges are, you know, $300,000 or $400,000. So it was a fail-safe, economical solution. And it came out of the work we did at SkyDome.
Yeah. And, you know, for me, I mean, there's lots of technology at a SkyDome, and I could talk about that and talk about how that's shaped maybe some engineering things, and it has in a lot of ways. But for me, the thing that came out of SkyDome was this whole way of working, you know, and in fact, from SkyDome on, it changed me and it changed my career in a way of working and working, you know, with architects in a close way and working with builders in a close way. You know, for me, that was the most important thing that I took out of that. And then I actually joined up Ellis Don after, you know, close to 30 years. And the CEO said, you know, I want you here and I want you to figure out this way of, we're pretty good at on time and on budget, but we got to work better and we've got to do things better than we have. And so I spent a few years trying to figure that out with Ellis Don. But to me, that's the biggest thing. And I'm really pleased to see it kind of coming around again. There's still some challenges with it, but that was the biggest one for me, was this team interaction thing and solving problems. And, you know, a little story, I was involved in a really difficult structural thing once in a meeting. And the person who helped it was a landscape architect, actually. And he sort of solved the structural problem that day. And, you know, it happens sometimes, this sort of spreading of ideas and people thinking and working together. It's great.
Okay, I would be remiss if I didn't add to that, but that was my first introduction to Ellis Don, and my career has been changed in much the same way, in that there hasn't been a year that hasn't gone by that I haven't done something with Ellis Don, including the last week opening the Ontario Court of Justice with Ellis Don on the latest DBFM with them. So I couldn't agree with you more, Chris. I mean, it's you know, working with, you know, good people really is important. With that, I think we're going to have to stop. I'd like to thank Professor Henshaw in this collaboration with the civil engineering at the faculty at the University of Windsor. Thank you very much for the invitation, and I think it's hopefully the students and the faculty have enjoyed this session. Professor Packer, thank you once again. Hopefully we'll do another SkyDome.
We'll meet again.
Chris Anders, as always,
Thanks.
happy birthday.
Oh yeah, that's right. Yeah. I started off when I was 28, you know, in the projects, and now I'm a little older now.
Enjoy the rest of the day. And
Yeah.
Philip Robbie, it was a pleasure having you on. All of the very best. And Chad, thank you. We'll see you soon. And for everyone that's on, thank you for joining us. All the best, and we'll see you another time. Bye now.
Take care.
Thank you.
Bye-bye.
Thanks very much.